So far, we've learned how to use sequential logic circuits to create a circuit that can store a bit of information, either using a latch or a flip-flop. What we're going to do in this video is investigate how we can use latches, specifically a D-latch, in multiple instances to create a piece of memory where we have multi-bit storage, and as an extra dimension, we have more than one word of multi-bit storage that we can use. Specifically, we're going to make a circuit that has 4 words where each word is 3 bits wide. Now here's the circuit, the complete circuit for this thing, and it's not meant to be the ideal circuit. Like you could definitely optimize this down so that it would use fewer gates or fewer, say, out-of-the-box components. But this version of the circuit that I've drawn here, I think, makes it a bit easier to understand. But as it stands here, it is relatively complicated. So I want to take a very step-by-step walkthrough of this circuit so that we can totally understand each of its components. So what we're going to do first is strip away everything except for the latches. So we can see the latches, and these are just simple clocked D-latches, are arranged in a nice matrix. So we have 4 rows, and each of those rows represents a single word, and each of the words contains 3 bits. So the leftmost column that we have is the high order bit, bit 2, for each of the 4 words. The middle column is the middle bit, bit 1, for each of our 4 words. And the right column is the low order bit, bit 0, for each of our 4 words. Now the first thing we want to be able to do with this, because it's clear, we have 12 bits of storage. So we'll pretend there is data in them, but we want to get that data out. And when we do it, we want to get it at a word level. So we need a way to read one specific word. Now, we can accomplish this by bussing down each of the individual bits that come out of our latches on a per column basis into a shared multiplexer for that column. So what you see down here is the lowest row, which is going to be word 3, gets its bit Q piped down into the multiplexer here at its data input of 3. So word 3 goes into position 3 of the multiplexer. The top latch is word 0, and you'll see that its wire connects itself to input 0 of that multiplexer, and 1 and 2 do the same respectively. And this is true at each column. So basically what we're trying to do here is say that we're going to have an output from this circuit where there's a high order bit, a middle bit, and a low order bit, so each of our 3 bits. And they are going to come from one row. And the way we determine which row they come from is based on these controller pins for each of the 3 multiplexers. Now they're labeled A here in each case, and that's short for address. And you'll notice that there are 2 wires. Now while I didn't label each of the wires to represent a 2-bit address, say A sub 1 and A sub 0 here, and I only did that for cleanliness of the diagram, what we must understand is that this is actually, A is actually 2 wires. It's a 2-bit address, and each of those go in to create a 2-bit number, 0 through 3. So if we put the address of 2 in here, each of the columns are going to have the multiplexer input on 2 routed to the output, and each of those is connected to row 2 of our bit matrix. So we at least have a way to route it, but this form of output is not ideal, mainly because this piece of memory, while it is 4 words of 3 bits, and we're accessing 1 word at a time, we're always accessing a word. So these output wires that come out of the multiplexers are continuously providing something for us to read, which may not seem like a big deal. If it's memory, we would want to get stuff out of it. But this will be bundled up in some kind of a package, which we might want to reuse or put in combination with one another, much like we have a matrix of latches here. We might want to take this 4x3 circuit and make a matrix of these so that we can have a more interesting memory still. Say, for example, 16 by 3 circuit created out of 4 4x3 circuits. In this case, we don't want each one of the 4x3 memories to be putting out some particular set of bit values. We're going to want something that sort of turns the individual 4x3s off. And the simplest way to do that, and we've seen this in other circuits, is to use an AND gate that we can use kind of like a gating transistor to allow the 3-bit pattern from a particular 4x3 out, let's say just this 4x3, or to not let it out, in which case we would turn off its AND gates and get a 0. And we can accomplish this relatively simply. And so we're going to have to introduce our first new inputs other than those 2 address bits to our 4x3 circuit. So we're going to need a input line that tells us that this chip is enabled. And so that's the enable, or sometimes it's labeled E, or sometimes CS for chip select. So we've got to have one of those. And if it's got a 1 on it, or it's high, logical high, then that means that this 4x3 chip is active and we're supposed to be doing something with it. If it is low or has a 0 digitally on it, then we are not supposed to be doing anything of substance with this chip, in which case we'll probably have it emit all zeros. Now, the second new input that we have here is the read-write pin. And if you look carefully at the way this is labeled, the R for read is lowercase and the W for write is uppercase. Whenever you see that kind of combination of a lowercase character and an uppercase character, that traditionally says that the lowercase character represents the action that you get when the line is 0 or a logical low. And the uppercase character tells us what we should expect the action to be as a side effect if we put a 1 or a logical high on that particular wire. So in this case, since the R is lowercase and the W is uppercase, when there is a 1 on this wire, we are saying that we are writing new data to the bits of some word in this circuit. And if a 0 is on this wire, then we are reading something from this circuit. So the output from these multiplexers, which should only be necessary on a read, not a write, or not when this particular 4x3 chip is actually being used, we can determine whether or not to gate those things out based on 2 conditions. One, this 4x3 chip needs to be enabled, and second, we need that read-write pin to have a 0 on it. So you see the AND gate creates that Boolean signal, a 1 or a 0, that I've labeled read enable to tell us that we're actually supposed to be doing a read with this device. And the inputs are a 1, or the expected input signal is a 1 on the enable or chip select, and a 0 on the read-write pin. So then what we'll do is we will bus that read enable across the bottom of this block diagram and run it into a layer of AND gates. And each of those 3 AND gates is going to have as its kind of data input that the read enable is gating through. It's going to have as its inputs the output of that bits, that column of bits multiplexer. Right? And so this is not too crazy, right? Great. So let's now consider what it would take to write something to this circuit, because getting stuff out of the bits is definitely something we want to do, but we hope that we're not just getting random stuff that was in there when these things turned on. We need to put stuff into the bits. And so we're going to have to engage the left sides of these latches. That's going to involve that little clock triangle and the data line. So the first thing we need to do is bust down the data input. So if this is a 4-word by 3-bit circuit, then we need 3 bits of data to potentially put in at any one time. We won't put in 6 bits of data. We won't write all 4 words at once. We will just make sure that we can do 1 word at a time. So we just need 3 bits of data. Data sub 2, data sub 1, and data sub 0, respectively, from the left to the right. And this is not so bad. So each data pin, I'll just pick data sub 2 here, that's on the left, you'll see that its bus comes straight down and it feeds that same value, whatever bit that is, into each of the 4 words high order bits. Now, what we absolutely don't want is for all 4 words to take on the same 3-bit value that we are providing at input at one time. So much like we had to figure out a way to choose which of the 4 words we were going to output if we were doing a read, we need to come up with a circuit that connects eventually to these clocks on each latch so that we are picking a single word to do a 3-bit input on, or 3-bit write, and then only have those 3 latches fire. So to do this initially, we're going to have to figure out which of the 4 words we want. Now, in the multiplexers, we use control lines that were labeled A, but that's really a 2-bit value. Got a little more space over here, so I've identified those 2 bits, A sub 1 and A sub 0, to make a 2-bit address, indicating that we're talking to word 0, word 1, word 2, or word 3. And the way we're going to isolate this is just using a basic 2 to 4 decoder. So we have our 2 bits of input, and if we put in the 2-bit pattern for the number 2, a 1 and A sub 1, and a 0 and A sub 0, let's say, then this output line, which we're calling word 2, will go high. All the others will be low. Now, one and only one of these will always be high. So we're going to have to make sure that this is not the only mechanism by which we enable a set of latches to actually take in new data, because we might be in the middle of a read, and then we definitely would not want to be pulling in new data. So we're going to have to isolate it with some additional work. So eventually what will happen is, from each of these 4 signals that identify which word that we're trying to utilize, we are going to get a 1 when it's for a particular word, and it's going to be bussed down a line like this and then run into the clock of each of its 3 latches. So you can see that pattern is repeated for each of our 4 words here, 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 and here. Now we need to look back at those 2 pins that we use for determining whether or not we really should be reading anything out of the circuit at all. We'll use the same 2 inputs, the enable pin, or the chip select, and the read-write pin, to determine whether or not we're supposed to be writing at this particular moment in time. So what we're looking for is to create this output called the write enable from a simple AND gate circuit that will have a 1 on it when we are supposed to actually be writing something to this 4x3 chip, okay, or 4x3 circuit. So we're going to do that, and you can see the 2 inputs to this AND gate both not having inversion bubbles. That indicates that we're going to do this under the multi-condition circumstance that this particular chip is enabled, or its chip select is high, and the read-write pin is high. Because don't forget that capital W, when the read-write pin is high, that means we are performing a write. Okay, so the last little bit is to combine the decoded business here about which word to use and the fact that we are supposed to be writing to this particular 4x3 circuit. And we bust down the write enable, going into a layer of AND gates. This is a lot like a multiplexer here. And so all of these AND gates will be ready to let data through, or let a 1 through, should its connected decoded address pin be a 1. But only one and only one of these, word 0, word 2, to word 3, word 1, only one of those is going to be high. So if our address bits are 0 and 1, then the word 1 output is going to be high. And that means this word 0 line will be low. And so a 0 will go into this AND gate, forcing a 0 out across its bus. And that means this whole set of latches will have a 0 on its clock, and it won't do anything, right? Down here on word 1, however, we're going to have a 1 coming in on the write enable, and word 1 will be high under that circumstance, and we have 1 ANDed with 1. It's a 1. And so the 1 gets bussed across, routed into each of the clocks, and it will have made that transition from 0 to 1. And so whether these latches are level triggered or edge triggered, that will give us the circumstance upon which we will read in each of the 3 data bits, data sub 2, data sub 1, and data sub 0, into our selected word of bits. Now we can put all of this together into a single circuit all at once, and then we have what we saw on the very first slide. All together, it's really quite a bit to take in. But we can walk through and figure out how each of these little subsystems work, because they're really doing two different things, telling us how to do a read, telling us how to do a write. And within both of those, we also have these two layers of AND gates. Each one has its own layer of AND gates, indicating how it is that we determine whether or not we really should be doing any writing or should be doing any reading, and from which word. Now, if we were to package this up in a nice abstract block to reuse in larger circuits, and we wanted to diagram them out, this is probably what this would look like. So we have to identify the primary inputs and outputs. And there really are only three outputs that we saw, and those are the 3 bit values that are coming out of whatever word we may be reading from. Now they'll always put out something, so if we're doing a write, they're going to be putting out zeros. If we're going to do a read, it's going to be data that's come from the storage of the latch matrix inside based on which word the 2-bit address pins point to. But the chip select or enable pin will need to be high, and the read-write pin is going to need to be low to support the read so that we get anything other than all zeros from these output pins. The only other input pins are the data pins, and they're only going to be utilized for anything when the chip select again is high, and the read-write pin is also high because the capital W indicates that we need a 1 there to do a write. So this is a lot to take in. Please rewind the video, watch it several times until all of the sub-features of this circuit seem obvious to you. And then once you have this little abstract block, you can create larger pieces of memory, say 16 words of memory, 256 3-bit words of memory, or you can align them serially to have words of memory that are larger than 3 bits. But this is the basic way all such circuits could be laid out.